So let's just do a schematic little type of an example whereby we try to, or we illustrate how to get Q. So let's keep it simple here, and I'm just going to illustrate the shaded area, the things that I'm calling the shaded area. That's going to be very helpful for you to create this shaded area so that you can get the right answer for Q. So it's very simple. First we get our point of interest, or are given our point of interest. So for this particular example, I have a T-beam, T-shaped cross-section, and my point of interest is given to be right there. So there's my point of interest. Here is my centroid, overall centroid, and like I say, this is just a conceptual example. Once I have my point of interest here, then I create my shaded area. Well, where's my shaded area going to be? My shaded area, based on what we just went through, you can go back and look at the derivation. My shaded area is the area above that point of interest. Right there. There's my shaded area. It's shown down here. I have that shaded area. Now you notice that it consists of two rectangles. So I'm going to break it into two rectangles. And I know where the centroid of a rectangle is, so I take the centroid of rectangle, I'm calling it rectangle 2. And I have, now this little piece here, well, it's got a centroid too. My centroid is the middle of that rectangle. That's 1. And so here's my overall centroid, which we find by normal means. And I take the distance from the overall centroid to each of the two centroids. So I get a D1, and then I get a D2. And so that's the calculation you have to make. Not hard, not difficult. And then I just take my area. So I have D1A1 plus D2A2. And that is my Q. Straightforward. So the key to being able to get the correct number for Q is to draw that shaded area to begin with, because you have to be able to determine what area you're talking about, and then get the D's. The D's are not difficult, but you have to make sure you don't make a mistake. So that's your Q. We'll put numbers on it later. Okay, this is another drawing, basically 3D image that's a little more clear. If you want to take a look at this, same derivation, and we get this result here. All right, so let's look at a case with numbers in it. And here is my beam cross-section. You can see it's made up of a number of laminations here. And I have a bolt down the middle that connects them all. So that is my beam cross-section. And I'm giving you the location of the point of interest right there. So your goal is to find the shaded area. So draw the shaded area now. And then find Q and B. So Q and B. So please pause the video and work this problem. All right, I'm assuming that you've done it. Well, what do we do to solve this? Well, we draw the shaded area. It's the area above the point of interest. Very straightforward. Now the centroid of this whole thing, it's symmetric. So where is the centroid of the overall beam cross-section? Right at the middle. So I don't have to do any calculations to get the centroid of the overall cross-section. And then I have two rectangles here. So I've got rectangle 1 rectangle 2, those are the centroids of those rectangles, centers of those rectangles, which is a centroid. So all I need to do then is get the distance from the overall centroid to the 1, that's a D1. The overall centroid to the centroid of 2 is D2. And then get the areas of those rectangles as well for the shaded area. So main thing, start with, you got to get the shaded area right. If you don't have that right, you're never going to get the Q right. Notice that all of these are the thickness distance of 0.1 meters. That means that center to center is 0.1 meters. To center, 0.1 meters. So once we recognize that, then it's pretty easy to see that D1 is 0.1 meter and D2 is 0.2 meters. So I know what D1 and D2 are. D1's 0.1 meter, D2 0.2 meters. So this distance here is 0.9 meters. This distance here is 0.5 meters. So A1 is 0.9 times 0.1. A2 is 0.5 times 0.1. So I now have my D1, D2, A1, and A2. I simply multiply them out, add them together, and I get my Q. 0.019 cubic meters. Meters cubed. It's not a volume. It looks like a volume. It's not a volume. It's, again, this area moment. And again, it has not much meaning. It's just it's not a concept. It's a definition. And the next thing is, what is B? Well, I get B of 0.9 meters. Why? Notice it's the width at the point of interest. Now, the problem here is that I have two widths at the point of interest because the point of interest is right at the interface. So one width is 0.9 meters. The other width is 1.1 meter. So I choose the smallest one. The smallest width at the point of interest. That is B. And this is the smallest of those two widths. So just be aware that that's what we want to get, is the smallest. Take a look at the derivation again if you don't feel comfortable with that. And like I say, D is always the distance between two centroids, the overall centroid and the centroid of one of the areas. Let's do another one. Like I say, VQ over IB, easy to apply. The only hard part is the Q and a little bit of the B, but B is not that difficult. But the Q is the issue. Now, I have said that you take the shaded area above the point of interest. Well, it ends up that you could also, if you wanted to, take the area below the point of interest. So, and it ends up that the calculation, the numerical value is the same. So this is what I'm going to illustrate here. So I have a T-beam, T-shaped beam here. And what we're going to do is draw the shaded area, get B, find Q, and we're going to use both the area above and the area below the point of interest. So here we go. So here's my cross section. Here's my point of interest. I'm giving you the point of interest. And so the first thing that we have to do to get the Q is we have to get, well, along the way we have to get the Y bar. So we had to do this with sigma. We need to do that here. So like I say, we break it up into 1 and 2, B1, H1, B1H1A1, B2H2A2, those are easy to get. Remember y bar 1, that's 0.5, so y bar 1 is 0.25. Y bar 2 goes all the way up here, so y bar 2 is going to go this full distance, which is going to be 0.5 plus 0.1, so it's 0.6. So y bar 2 is 0.6. And then y bar is y bar 1A1 plus y bar 2A2 over A plus A1 plus A2. I get my y bar overall. Okay, so my y bar overall, now there's a little bit of a trick to this one in the sense that my y bar overall is right in here, which is 0.46538 if you want to carry a lot of digits there. No matter. Okay. But I'm going to do this two ways. I'm going to take the shade. So here's my point of interest. And then I shade the area above that point of interest. And that's that. Down here, I'm going to do it. There's my point of interest. I'm going to shade all of the area below the point of interest. Down there. See if I get the same result. Little bit of a trick. A little bit of a complication I haven't explained yet. Okay, so what I have now is I have this area here, and I've got this area here. So I need to find the centroid of both of those rectangles. So the centroid for that rectangle is the middle of that rectangle. And the centroid for that rectangle is the middle of that rectangle. Okay, so if I look at this, given my dimensions here, I know that, well, this is only 0.2 from the 0.2 feet from the base, but my y bar is 0.46538. So my overall centroid is pretty close to the interface between the two rectangles, and that means that the centroid of the lower rectangle is where? Well, let's see. So, well, let's see if we can figure it out. This distance is 0.3. The centroid of that then is 0.15. So my centroid for that bottom rectangle here is 0.2 plus 0.15. So plus half of 0.3. So is 0.15. So 0.2 plus 0.15 is 0.35. So I'm running out of space to show this. But, and it's a little bit crowded, so maybe I'll try to resketch this. But when I'm looking at, let's just look at the bottom piece here. So if my bottom piece is here, my point of interest is down here, that means that my centroid of the upper rectangle is there. My overall centroid is here. So what I'm finding is that this total distance is my y bar. This distance is 0.35. So the difference between those two is, the 0.46538 minus 0.35. So that is my D1. So if we look at this, we get my D1 as being the difference between those. And so it's 0.46538 minus 0.35, a little bit tiny here. So I get a D1 of 0.11538, but because it's below the centroid, it's negative because we're measuring upward as positive. So in this case, we're worried about the D, the sign of the D, which we didn't have to worry about before because D ended up to be squared. So if that distance is, if we're measuring below the centroid, the overall centroid, I have to use a negative. So my D1 is negative 0.11538. A1 is 0.3 times 0.1. Well, that's easy. And then for my second area, that's easy to get. You can get the D2 is this, and it's positive because it's above, and so I get a D2A2 for that. So my D1A1 is negative, D2A2 is positive. I add them both together, and this is my value for Q. Okay, but now if I wanted to do that, I can take the area below. So the first one I did was the area above. Now I'm going to take the area below. Well, it's a little bit easier calculation. So all I need to do is get my centroid for my little bottom rectangle. And I know that that's a distance of 0.1 from the base. And so the distance between the two centroids is 0.36538. So I get D3, 0.36538 times A3, which is 0.02, and I get 0.00731. There's a little bit of round off. So in other words, these two numbers are the same. It didn't make any difference whether I took the area above or area below. So just to let you know, you can choose the area above or below. It doesn't matter. Choose the easier one, okay? Obviously, the easier one of this, for this particular problem, was down there. Okay. So let's look at a complete problem here. We have this beam, laminated beam here. I'm saying to find the shear stress at the point of interest. Well, here's my point of interest right there. This is my beam cross section. So my point of interest is right there, right at that level, as I've shown it. Okay, so that's fine. All the dimensions are given, and I'm not going to go through all of those. I'm just going to, so here's my point of interest. Let's find the shear stress of that point of interest given this loading condition and dimensions and everything. Well, it's pretty straightforward. This is 10 kilonewtons, so I have reactions of 5 kilonewtons each. Very straightforward. I draw my shear diagram. Looks like that. Up 5, down 10, over, up 5. So what do I get at my point of interest? Well, my shear force from the shear diagram is 5 kilonewtons at the point of interest, okay? That's easy. So all I'm doing is filling in this expression, tau is equal to VQ over IB. And like I said, the V, the I, and the B, they're easy. So it's the Q that's the only hard part. So let's do the easy ones first. 5 kilonewtons from the shear diagram, 5 kilonewtons. I is what? Well, this is a rectangle. So life is easy. Forget the laminations. They don't make they don't make a difference. The laminations are just illustrating where our point of interest is. But so it's a rectangle. B is 0.1. H is 0.6. So 1/12 BH cubed, 112.1 times 0.6 cubed. That is my I, so I put my I there. V, 5 kilonewtons, we put there. B, the width, well, B is the same everywhere, so that makes my life very easy. So that is not hard. So B is what? 0.1. So I've got V, I've got I, I've got B, got everything. They only took 2 seconds to do. The only hard one is the Q. How do I get the Q? I have to create my shaded area. Well, I get my shaded area is the area above the point of interest. So there's my shaded area. It's one rectangle's worth. I get the centroid of that rectangle, and I have my overall centroid, which is dead center, and that distance is 0.25. So my Q is D1A1, so it's going to be 0.25, and the area is, you can get it as 0.1 times 0.1. So that gives me a Q of 0.0025 meters cubed. I multiply all that, so I put the Q goes into here, and I simply do that calculation. I get 69.4 kilopascals. All right, let's look at another one. Now I like to talk about the bolts, because here's what I'd like you to envision that I haven't quite described completely. But let me go back to our original discussion of this particular problem, where we learned that, when we bend this laminated beam, what happens? We get sliding between the laminations. Well, that's when the laminations, of course, are, not held together. But, one way to hold this together, I sort of like this image, one way to hold the laminations together is to, put bolts through here and hold this thing so that the laminations don't slide. Now, my question for you, what I'd like you to think about, is suppose these bolts are weak. For the sake of discussion, suppose they are weak. So envision, bolts made out of sponge or something like that, for the sake of discussion. And so in other words, not weak enough to resist the sliding. Well, what's going to happen if the bolts are that weak? Well, what's going to happen is that these bolts are going to shear off. So in other words, if I get sliding, what's going to happen is that, for instance, I have a bolt here, and if I get sliding there, what's going to happen is that bolt is going to do something like that. It's going to get sheared off because of the sliding that takes place between the laminations, and if the bolts aren't strong enough to resist that, they get sheared off. So that's what we're worried about. We're worried about this sort of sheared off behavior that can occur if the bolts aren't strong enough. So we need to figure out if that's going to happen, or how many bolts do we need to prevent that from happening, or how strong do the bolts need to be. So let's take a look, and we can get that information from our shear stress calculation. So here's my T beam, and I'm going to put my bolt. My bolt goes from the top through into the web of this T-beam. And what I'm worried about is shearing of the bolt at the interface here. So my point of interest becomes at that interface right there, because I'm worried about this shearing off. So in this particular problem, let's read it. It says each bolt can resist 7 kips of shear. How many bolts are needed? What is the spacing? S. So let's show you how to do this problem. Okay, so what we're looking at is, here's my beam, this is the cross section. I have 20 kip loads here, so everything's symmetric and the reactions are 20 kips each. And I've got bolts and, going across this beam. And my question is, given, these bolts, each bolt can resist 7 kips of shear. So what I want to determine is, what is my spacing S along here? What should the spacing be for those bolts? That's one of the things we want to determine. The other is, so how many bolts do I need? So, okay, how do we do this? Well, we first start by finding, first we know the point of interest is there because that's where it's going to shear off. So that's my point of interest. So you have to recognize that. So if I give you a problem, I'm not going, and I say, how many bolts do we need? You have to figure out where the bolt is going to shear off. And that's going to be at the interface there, or an interface. Okay, so let's just get going with getting what I want then is, what is the shear stress at that interface? So I'm not going to go through, I draw the shear diagram up over. I draw the moment diagram, that's my area, so I go up there. There's nothing in this region, which means I go straight across on my moment diagram. And then that area is negative 100, I go down. So just to let you know, notice there's no shear here, V equals 0. That means that in this region we call that, we call that pure bending. There's no shear there, so that is a region of pure bending. So that's just a term that you should be familiar with. When the shear is 0, then I have pure bending. Okay, so we're going to, that's our expression, VQ over IB, that I want to fill in. Now, the other part, okay, so I know where my point of interest is on the beam cross-section because that's the interface. But how do I determine what is my point of interest along the length of the beam? So this is similar to what we had to do with sigma. We had to find the point of interest sometimes. So how do I determine it? Well, I look at my shear diagram and I figure, where's the shear the maximum? Well, either up here or down here is where it's a maximum. There's no shear here. So to be honest with you, in this region, we don't really need any bolts for shear resistance because there is no shear. Tau is 0, but we're just assuming that that we're going to space everything equally anyway. It just keeps it simple. Space all the bolts equally. So I pick a point of interest that gives me the shear of 20 kips. I could have chosen over here, it's fine. We're not that concerned about the sign for this. Take the maximum absolute value. So, in other words, you could take this one, if it could be negative, but okay, so V is 20 kips. We have previously determined the moment of inertia for this. So we've already determined it. I'm not going to redo it. You can find the centroid and the moment of inertia. So we're going to leave it at that. Or, well, let's see. Maybe I actually have the calculation here. Yeah, I do. Okay. I think we've previously done this problem, but we'll do it again. And so I'm just going to let you pause the video to figure out what the Y bar is. And the I is, I'm not going to go through this again. Okay, so we have our y bar and I. So the I goes there. So we found the V and the I. How about the B? Well, here's my point of interest. Well, how do I choose my B? Well, the B is the smallest width. There's two widths here. The outer and the inner width is 2 inches. So I'm going to take the 2 inches. So we've already filled in very easily 3 of those terms. The only one left I have is my Q. Now I'm going to use my y bar as 5 inches. That means that that the overall centroid is at a distance 5 inches from the base. My shaded area is simply this area up here. And so I want the distance from the overall centroid to the centroid of that shaded area. Well, that shaded area actually is A2. So by coincidence, to a certain extent, there's my A2 and so my D for my Q calculation is D2, which is 2 inches. So in other words, this distance here is 2 inches. So my Q is D2A2, and so that becomes 24 cubic inches. So I can put that in here, and now multiply this out, I get my tau at my point of interest, 1.76 KSI, kips per square inch. Okay, now what does that mean in terms of how many bolts I need? Well, this is a plan view of the beam here. This is a plan view. So I'm looking down on the beam, and I have these bolts going into the beam. Now, I'm going to introduce the concept of tributary area here. And what is a tributary? Well, you know the word tributary possibly from a geography class you may have had, where you have a tributary to a river. What is the here's my main river, and these are tributaries. They come into the river. Tributary, the root word is contribute. What the small stream contributes to the big river. Small stream contributes to the big river, so they're called tributaries. Well, what we're looking for here is what contributes to the load on that bolt. What area? So we're talking about a tributary area. What contributes to what area? Well, if I'm looking at a bolt here, and I have another bolt here, and I have another bolt here, well, the bolt in the middle is responsible for halfway in between, the area halfway in between. So my tributary, what we call our tributary area, is halfway to the next bolt, and then halfway to the other bolt, halfway to the bolt on the right, halfway to the bolt on the left. And so the stress in this region contributes to the force in this middle bolt. So what I'm interested in is this tributary area here, and that stress that has got to be picked up by that bolt. So I call that distance ends up to be S. Why? Because I'm spacing my bolts at a distance of S, which means that the center to center distance is also S. So this tributary area has dimensions of S times B. It's a rectangle, S times B. So that's my tributary area for the bolt. And you remember, force is equal to stress times area when the stress is constant. And here we're saying the stress is constant because we're picking, that's what we're saying when we take our, it's a little bit of an assumption, when we take our shear force at the greatest on the shear diagram. So we're just assuming that even though that even though that shear force does not exist over the entire beam, so in other words, that shear force only exists there and doesn't exist there, just for the sake of keeping everything simple. And we're going to assume, to be conservative, that this acts over the entire beam, and we're going to put the bolts at an even spacing based on the greatest shear. And so what we find is that the force is stress times area, tau SB, times tau times the tributary area. So tau SB is the force, that's the force. So what do we find? The allowable force in the bolt we're given for this problem is 7 kips. So that's the most, so that now that's allowable, so there's a little bit of a safety in there. And so the force in the bolt is tau SB, or the allowable force in the bolt is tau SB. And so I can solve for S. S is FB over tau times B. So the 7 kips divided by the 1.76 times 2, and we get, you can check the units out, we get unit cancellation here, and so our answer is that the spacing is 2 inches, and our beam is 15 feet times 12 inches per foot. Our beam is 180 inches in length, so my number of bolts is 180 inches divided by the spacing, 2 inches, I get 90 bolts. So, yeah. And that is how you do a bolt problem. Now let me just make one other point here. And that is that, since we know that tau is equal to VQ over IB, we can manipulate this tau times B. Tau times B is VQ over I. Well, there's tau times B, there's tau times B. I can put that in there. And I can get the spacing then becomes simply FB times I over VQ. So there's a little bit of a shortcut. We don't have to deal with the B. So either way, you can simply use that equation for the spacing, or you can do it this way. Either way is fine.